All right, let's do it then. Thank you for coming. So this is for the students. The faculty in the math department meet a few times a semester just to chat with one another about research projects that we're involved in. In the math department, we don't usually work together on research projects because our areas of research are mostly different from one another. And so, for instance, I know all four of these people write and publish papers, but I've never read any of them because when mathematicians are in different areas, it's very difficult to understand. And I assume they've never read my papers because they would not be easy to understand. But I'm going to try and give you a fairly understandable version of this paper. It's called At Most N-Valued Maps. And this is a paper that I wrote with Daceberg, Gonçalves, and Robert Skiba. Daceberg is at the University of Sao Paulo in Brazil, and Robert is at the Copernicus University in Torun, Poland. I have written a few papers about what we call n-valued maps. This is a type of multi-valued function. And this, here you can see this cute little arrow here. For ordinary functions, we write like an arrow with a arrow. For multi-valued functions, there's this thing, which means f is a function from x into x, but in the image of this function, it has several values. And it's called an n-valued map if it's a function where the number of values is always equal to n, where n is just a whole number, all right? So they look something like this. This is a three-valued map of the circle. So it has three values because if you look at each x, like in the bottom in the domain, and look up, it has three different y values. So that's called a three-valued map. Of the circle here, and most of what I'm going to talk about today are maps of the circle. The domain here, it looks like just sort of an interval, but I'm thinking of this topologically as the circle, which means this interval makes a circle if you glue the end point to the starting point. And so in order for these to be legal continuous functions, every time the curve goes off the right, it has to come back on the left at the same place, kind of like Pac-Man or when in asteroids. And same goes for the top and the bottom. So the domain here is the circle. I'm going to draw it like a straight line, but you imagine that the right side of it is glued to the left side, just because otherwise it's hard to draw the picture of this. All right, S1 is the interval with endpoints identified. This is a very common thing in topology. Topology is what is my main research focus. N-valued means exactly n. So when I say like three-valued, every x has three values of y. That means three-valued. These we also call in the paper equicardinal. Cardinal is the fancy word for like amount of things, and meaning every x value has the same amount of y values. In that example, it's 3. Sometimes one of these equicardinal, this is two-valued. Sometimes equicardinal map can split into single-valued maps. Like this one, every x has two y values, but you can actually kind of split that apart into just two single-valued functions. This is one way in which you can sidestep the issue of continuity of a multi-valued function, because this is a two-valued function, but actually it's just two single-valued functions put together. So certainly that ought to be continuous. Like everybody knows how to handle functions like that because they're just ordinary continuous functions. All right, so we call this, when this happens, we call this the map splits into single-valued maps. But this one is an example of one which does not split into single-valued maps. This is also two-valued. And you may think, can I just do that? Those are the two different functions. This is a problem, though. Remember, I'm considering this to be a map on the circle, which means when it goes off one side, it has to come back on the other side in the same spot, and this one doesn't. This is actually not continuous as a map on the circle because the value down here does not match up with the value over here. When you go around the circle, it ends up at a different point than where you started. So this is an illegal splitting of that two-valued function. In fact, this is a two-valued function on the circle, which it's not possible to split into two single-valued functions on the circle. All right, so anyway, what I really want to talk about in this paper, and the title of the paper is At Most N-Valued Maps. That means something like this. So this is now, we call this at most 3 values. That means for each x in the domain, the amount of y values is at most 3. So it could be 3 or 2 or 1. It's not allowed to be 0. But That's what I mean by at most n-valued map. So that's a at most 3-valued map. This is like a 3-valued map, but it has some like crossings where maybe it goes down to 2. And it could be that all 3 lines cross at once and it goes down to only 1 value. That's called the at most 3 value. So how do we handle such multi-valued functions? All right, this particular one is fairly easy to handle because if you look closely, you will realize it actually splits into 3 different continuous single-valued maps. And so this particular example is fairly easy to deal with. Now, my approach to all of this, like when I say easy to deal with, mostly I am thinking in terms of investigating the fixed points of the functions because this is what I'm interested in topology in general, although this paper is not about fixed points at all. But anyway, a function like this can be treated just using ordinary techniques for single-valued functions because it's just 3 of them put together, all right? And actually, this generally will happen in a lot of cases. This is called the splitting lemma that was proved by Helga Schirmer in the 80s. It says if the domain is simply connected and then this is at most n-valued function, then it automatically splits into a union of single-valued maps. The important part is this, simply connected. That means topologically that the domain has no holes in it. So actually, this is not true of the circle, which has a big hole in the middle. But it is true of, say, the real numbers. So the real numbers is simply connected. Also, like a closed interval is simply connected. And so if the domain is R, what the splitting lemma means is every n-valued function splits into n different single-valued functions. And from my point of view, that means it's not very interesting. I'm interested in talking about the interesting case where it really is a multi-valued function. You can't break it apart into individual single-valued functions. All right, so all the interesting examples, at least in dimension 1, are going to require the circle as the domain. And that's why all the examples I'm talking about basically the whole time have the circle as the domain. The whole situation is not very interesting if you use the real numbers as the domain. Okay, so we have this notation for the general class of all at most n-valued maps. This is I'm going to call C. All of the continuous at most n-valued maps. Let's talk about continuous. As she said, the meaning of continuous is a little tricky in this setting, and we have to mention something about this. So this is the typical topological definition of continuity. It says that if you have an open set in the codomain, the preimage of that open set is open in the domain. This is how we define continuity in topology. It's the same as the epsilon delta definition if you're using subsets of R. The problem is the meaning of this preimage set is ambiguous if you're talking about multi-valued functions. For example, like, okay, everybody knows that's what the preimage means. It's all the points in the domain which end up in the set U at the end, all right? For a single-valued function, that's what it means. But if f is a multi-valued function, that means f of x, what I see right here, is not an element but a set. And so what are you going to do with this? How do you make any sense of this? We can do a fairly simple modification. Anyone want to guess what we're going to say? How do you rewrite this? I want something like that, but it makes sense if f of x is a set, not just a point.
You're going to put this subset.
Oh, yeah, she's giving me the hand signal for subset. I didn't understand this. Yes.
Seriously?
So we can't say f of x is an element of U because it's not an element, it's a set. So we could say that, all right? This is the natural thing to say. There's actually a less obvious but just as good thing that you could say. An alternative is this, that the set f of x has non-empty intersection with U, all right? So this means f of x is completely inside of U. This means a part of f of x overlaps with a part of U. And actually, these are just 2 different ways to generalize this element sign. And there's no reason to prefer one versus the other. And they give you 2 different notions of continuity. All right? If f of x is a set of a single element, then these are actually equivalent to one another. But if f of x is a set of more than one element, then these are 2 different things. They lead to different notions of continuity for multi-valued functions. So there's actually 2 types of continuous. There's the one where you use the subset, and there's the one where you use the non-empty intersection. All right? And maybe you've heard these names, I don't know. We say that f is upper semi-continuous when this is...
An example to our it differs? No.
I'm about to show you an example. Yeah,
Oh my
I'm
God.
telling you the names first. You got to know the names.
Okay.
I can never remember the difference. One is called upper and the other is called lower, and I immediately forget which is which. But to me, these are not very good names. One should be like subset, and the other should be intersection or something like that, but they're not. This is upper and lower. So the upper is the one which uses the subset. The lower is the one which uses the intersection. And they're two different things. They are different. Here's an example, Janet. This one is upper but not lower.
No, but I don't. It's not on S1 anymore, my example.
It's not. Yeah, actually, this is just R to R. Yeah.
to R.
Two values at most. No, actually, there are exactly two values everywhere. The weird thing happens in the middle, but it is still just two values in the middle. This one is upper semi-continuous, but not lower semi-continuous. All right, so they are different. Actually, I don't like that one. To me, this still doesn't look continuous because it has this weird point in the middle of nowhere up there. So still too weird in my opinion. Typically, the papers that are written, at least that I'm familiar with, they don't want to deal with this weird distinction between the upper and the lower. They say a function is called multi-continuous, or I'm just going to say continuous, when it is both upper and lower semi-continuous. All right, so it's a stronger condition than either of those. And that example that I said before, this one here is, for our purposes, this does not count as continuous. All right. Okay, so when I say n-valued map or at most n-valued map, I always mean upper and lower semi-continuous. All right, so that one right there does not count as continuous. It is, what did I say? It is upper but not lower, or maybe the other way around. But it's not good enough for what we're going to talk about today. All right, informally speaking, if you want to know, like generally speaking, what does it look like when it is continuous versus what does it look like when it's not continuous? It has a graph, so for it to be continuous, it has a graph that looks more or less like a bunch of continuous lines like this one. This is both upper and lower semi-continuous. And this is at most 3 valued because somewhere, like right here, you can see there are 3 values. Elsewhere, there are often 2. Sometimes there's only 1, all right? This is continuous as an at most 3 valued map. The lines are allowed to cross each other or merge together sometimes, like right here, these 2 lines kind of continue together for a while. No jumps or holes or ends, like the line is not allowed to just kind of dead end in space. All right, this is an example, this is a silly example of one which is not continuous. You can see, so this is not allowed, this sort of the line just ending in the middle of nowhere. This silly face is not allowed. Actually, if you look carefully at the definitions, this doesn't really look like an end, but it is a portion of the graph which just sort of like appears out of nowhere. If you imagine moving from left to right here, this part of the graph didn't exist and then it just suddenly existed. That's not allowed in a continuous function. And also this vertical segment, of course, is not allowed as a n-valued function. Yeah, this now there are infinitely many values right here, and I don't want to talk about that. Yeah. I suppose this does not break the continuity conditions. It breaks the finiteness of the set of values. All right. Generally speaking, these maps are a little hard to get a handle on. So if you look at papers about these kinds of things, the literature has several classes of at most n-valued maps with various extra structures to make them a little easier to deal with. And we have identified some classes which we call by these letters, U, F, S, and W. And this is my goal for today. I don't know how far, if we'll get through all of them, but I want to talk about at least a little bit about each of these different classes. When we started thinking about this, Dassyberg and I were at a conference together in Belgium in 2023, and we more or less immediately came up with this F and S. I mean, we didn't invent these, but we know papers in which they discussed these 2 classes, and we realized like these are at most n-valued maps, but they have some extra kind of properties to them. And then more or less like in the next couple months, we realized that this U set was important. And then much later, like maybe a year later, we got in contact with Robert, the third guy. And he's an expert in this other thing called this W class, which Dassyberg and I had never heard of before. But I gave kind of a very preliminary talk about this in Poland. And one guy in the audience was like, hey, you should talk to this guy, Robert. He knows about something or other. And I was like, I never heard of that. And he said, well, yeah, but I think it might be similar to what you're talking about. And it ended up being very similar. And so I read Robert's paper, and then we emailed him and said, hey, you want to join in on this paper we're working on? So anyway, let's talk about this U. U is for union. So the simplest type of functions, and this is what we already kind of talked about before, unions of equicardinal maps, like this one right here. By itself, it has some of these crossings, but you can break it down into two different, this is a 1 valued, this is a 2 valued, but they have no crossings individually, all right? And so this one is fairly straightforward to deal with. This is the class which we call U, unions of equicardinal maps. And the first big question is, can you always break these down into a union of equicardinal maps? And the answer is no. So you might, this is actually what I thought. I have no idea how hard this is, but I want you guys to try and think about this. You can chat with your friends nearby. This is the audience participation section of our evening. This is something that I had a chat with. I remember at this conference, I was talking with Dassyberg one night. I asked him this question. We weren't really sure what the answer was. And then I woke up in the morning, and by then I had sort of thought about it in the back of my mind, and I had an example in mind. So what I would like for you all...
No, but hold on, before you give us that.
Yep.
The equicardinals, what is it? Just...
That means they're these ones which have no crossings at all.
Oh, no crossings.
So the question is, if you start with any function like this, which maybe does have these kinds of crossings, can I break it down into a union of 2 or maybe more than 2 things individually which do not have any of those crossings? That's the question, all right? The answer is no. So actually there is an example, and it's not all that complicated. Like I said, I have no idea how hard this would be for you all to come up with, just because I don't know. I feel like this was kind of hard for us at first because we didn't know what the answer was, and we didn't even really understand precisely the question we were asking at the time. So, this is how math research goes. Here's a little inspiration. It's like this one can break into 2 maps like that. This one here, though, are you sure that this one can or cannot break into other maps with no crossings as unions? I would say it's less clear. In fact, I happen to know because I worked it out. This one actually you can break it down into a union of 2 other functions without crossings. But this is what I would like you to try and think about. I will give you 4 minutes on the clock until the clock says 3:25. I have no idea if this is enough time or not, but see if you can think of an example that it will look kind of like this, I guess, but it cannot break into 2 separate maps with no crossings. This is your job. Talk to your friends and coworkers and students. I'll give you a hint. This is only possible for functions on the circle. So what you draw, it needs to sort of go off one end and come back the other end. Although my example does not go off the top and come back the bottom. But it does, the fact that it goes around is important. That's what I'm saying. This is the kind of thing that I thought about like in the back of my mind for several hours. I don't know if I had been really focused on thinking about it, would I have thought it was easy? I don't know. All right, your time is up. Any examples? I saw some people working on it. Great job, everybody. It's okay if you didn't quite finish up. This is my examples that I came up with the next morning. It doesn't look all that complicated. Does anybody think you can write that as a union of...
No,
We have the line across the top, the line across the bottom, and this kind of diagonal thing. Now, the diagonal thing doesn't exist just as that diagonal part, but you could take, say, the bottom bit, and then the diagonal, and then the top bit, right? This is what I refer to as the rookie mistake. And I think actually, when I first showed this example to my delightful co-authors, they're like, "What? Can't you just do this?" Actually, there's a problem with this. What's the problem?
Because it doesn't loop around.
Yeah, because this one here is not actually a legitimate map on the circle because it doesn't match itself up. And I mean, it's maybe not obvious, but we proved that you really can't do this. So this is a bad idea, right? That is not allowed, and there is no other way that you can actually make this work out. All right. Any thoughts about that? Were you about to come up with this?
I am thinking, I'm sorry, because I'm slow.
No.
The top of the square.
Oh, way up here?
Should have been red.
Yeah.
It is red.
Right, because it's the same as the bottom of the square. Yeah.
Yeah, it's really hard to.
Mm-hmm. By the way, for the students in the audience, this is very typical sort of conversations that people have while doing math research. It's a lot of like, wait a minute, oh yeah, okay. Oh, no, all right. It's a lot of that kind of discussion. Maybe probably, if you work on your homework with other people, it's probably the same way. But, yeah. All right, okay. So anyway, this means the conclusion is this class, these unions of maps, is a proper subset. Remember, C is just all continuous at most n valued maps, all right? They are not the same. There are some at most n valued maps which cannot be written as unions, like that one that I just showed you, all right? So anyway, the beginning of this project was we sort of scoured the other papers about such things and tried to figure out what are the relationships in these other classes? Like, how do they fit into? We have U, which is like a small bunch of stuff, which is contained in a bigger universe. But what about these other things, and how do they fit? It turns out this is the main theorem from the paper. So that's what we proved about all of these different classes. So I'm going to try and tell you a little bit about the S, the W, and the F, and how they all relate. So the U is actually like the smallest and most most regular class of these maps. And then these other ones have kind of increasing complexity. The S and the W are two different classes which had appeared in papers before, but we proved that they're actually the same, which was not known before, I guess. So anyway, let's talk about the S. These are called the symmetric product maps. So if I do have a multivalued function with at most n values, you can think of this as just a single map x into y to the n. Y to the n means the product of y with itself n times. That is tuples. You know, if n was 2, this would be pairs of points. So if I tell you, like, I'm imagining a function which has 5 values at all the points, you could just say, well, okay, that's the same. If you're giving me 5 values at every point, that's just the same as mapping from x into y 5 times, right? And so a multi-map with at most n values can be modeled as a single map into here. There is a difference, though, and the difference is the ordering. Like, this set, y to the n, is the Cartesian product of ordered pairs or ordered triples or whatever, all right? But when I'm talking about a set with at most n values, that's an unordered object. So there is a slight difference between these two types of things. And so in order to kind of correct this, we do a quotient by the symmetric group. So this as a topological space, or you could think of it as it's the set of all n tuples, but I disregard the order. So rather than taking ordered pairs or ordered triples, I am considering sort of equivalence classes which make them into unordered pairs or unordered triples. And this is called the symmetric product, the n-fold symmetric product. And it's written this way, SPN of y. All right, this is for all you folks out there when you learned about set theory and everyone started talking about products is a set of ordered pairs. And you're like, okay, but what about if I want to make unordered pairs? Nobody ever asked that, but this is what you would do if you wanted to do that. This is how you get unordered pairs. You start with all the ordered pairs, but then you do this equivalence relation where you disregard the ordering. This is called the symmetric product. Symmetric product because you're not considering any ordering anymore. All right, it's just like y to the n, but the points are considered as unordered, and possibly with repeated elements. That is allowed. Because, of course, in y to the n, you are allowed to repeat the coordinates. You can have something like 1, 1, all right? Okay, so anyway, we can view one of these, then, as a multi-map where the image of each point is an unordered set of n or fewer elements. And this seems, on the surface, to be the same as what I've been talking about all along, as an at most n-valued map, all right? So anyway, this kind of function, the kinds of functions which go into SPN, those all count as at most n-valued maps. The next question is, again, are these equivalent? Are they the same type of set? Are they equal, right? That is to say, is it true that every at most n-valued function can be written as one of these symmetric product functions? They are not equal, and again, the counterexample is this. This map is at most 3 valued, as we know, but actually it turns out you cannot express this as a function, a continuous function that has values which look like unordered triples of points. And why not? Remember, this SP3 of x would be unordered triples. I'm going to write them with these sort of square brackets just so that I remember that it's not an ordered triple, it's an unordered triple. If you think about it, if this really was a legal function into this unordered triples space, then the picture actually is a little ambiguous. For example, what exactly is f of 0? That would be this set, those 2 points, all right? But I have to consider those 2 points as an unordered triple, and it's ambiguous. Is it, I'm writing this as the interval 0 to 1. When I look at those 2 points as an unordered triple, am I talking about 0, 0, and 1/2? Or am I talking about 0 and 1/2 and 1/2, right? If it's an unordered triple, but I only have 2 different points, then one of them has to be repeated. And just by looking at the picture, you can't tell which one I mean, all right? So the picture actually is no longer enough to specify the function entirely. One thing that is true, actually, either way is going to lead to a contradiction. And if you consider the point in the middle, that actually is not ambiguous, because there really are 3 different points. Consider what happens if you follow this point a little bit to the right. I mean the domain point. Just push everything to the right. You will see the 2 upper points will come together when those lines meet at the top. And so actually the value, when I get to the end, actually it's not ambiguous. It must be 1 on the bottom and 2 on the top, because of the continuity if you follow these 3 points to the right. It must be 1 at the bottom and 2 at the top, all right? But maybe I said before, either assumption will be contradictory. Maybe you can see where this is going. If I instead follow them to the left, then the point all the way on the left has to be 2 on the bottom and 1 on the top. But because this is supposed to be the circle, this is a problem. The thing on the right, whatever I end up with on the right has to equal the thing on the left, or else it's not continuous. And so if you follow this point to the right, you will see f of 1 equals that, 2 up top, 1 on the bottom. But if I follow it to the left, I see f of 0 equals that, 2 on the bottom, 1 on the top. And this now is no longer continuous on the circle because it has to be the same value on the right versus the left, all right? So this is not continuous, which means this whole thing cannot be expressed as a continuous function into the symmetric product SP3, all right? That's a contradiction. Okay, so this is a set-valued map with at most 3 values, if you consider the values as sets. Those sets can either have 2 values or 3 values. But it is not a legal map into this symmetric product space. All right. So that means that this symmetric product class is strictly smaller than C is just the all continuous at most n-valued functions. All right. What about S versus U? This is what Janet was asking about before. This is our result is that U is a proper subset of S. Maybe I'm going to speed up a little just so I can get through what I wanted. This actually is what Janet was just asking me about. I had planned on just saying, yeah, it's pretty easy to see that this is true. The idea is if you have a function which breaks apart as a union like that, then you can just define this. So put these symmetric product brackets around everything. And this will be a continuous map into the symmetric product. You have to be a little bit careful about weird things that can happen when the lines cross one another, but everything works out okay. Sorry to abbreviate the part that you had actually asked me about. So anyway, this U set is a subset of the symmetric product. And in fact, there are symmetric product maps which cannot be written as unions of equicardinal maps. And this is an example. This is actually, Robert came up with this nice example. So here, this one's a little weird. The domain is not a circle anymore, but a shape that looks like this. So the interval in the middle is a real interval, but then the 2 ends of it have their ends glued together. So the domain is this kind of, I don't know what that's called. But anyway, this is an example of this one can be written as a symmetric product map, but it cannot be broken down as a union. Again, you might think, can I just sort of take the upper part here across the middle and then the upper part here? That's not a legal circle map because just on this part, it would not correctly match up from one end to the other. So anyway, that's an example that shows, yeah, this is a map into the symmetric product, the twofold symmetric product, but it's not a union of equicardinals. Here's a little explanation, but I'm going to rush a little. So far, this is what we've shown. There are actually 3 different classes, and they are properly contained in one another, all right? One more class. This is the class that Robert was an expert on. I had never heard of it before, and I think Dasseyberg has never heard of it either, but I don't want to speak for him necessarily. Robert wrote his PhD dissertation about weighted maps with weights in the natural numbers. Yeah, we had never heard of this, but Robert is an expert on this. And this is the definition. I suppose I'm giving you a intuitive version of the definition. It's a multi-valued map where each individual value is tagged with a natural number, which is called the weight, and those weights are non-zero. For instance, something that looks like this. So this is just like one of my other examples, but I am additionally giving particular number values to every point on the graph. And the weights must be assigned continuously. That is to say, if you move just across one of these arcs, the weights will stay the same. So each individual point here has weight 1, and they are additive at the intersection. So here, when 2 1s come together, it makes a 2, and then when this 2 splits apart again, those will be 1s each. All right, this is called a weighted map. So it's another kind of multi-valued function, which now has these extra numbers, all right? That one that I drew before, actually, you can assign these weights to it in this way. It's not, actually, this will take you, it's not hard to do, but it'll take you a few moments. If I showed you that complicated thing and said, show me how you can put the numbers on here, you have to choose them kind of carefully so that when the lines come together, the numbers add up. But anyway, this particular one, you can draw the numbers. Now, when I'm saying all this, the notion should occur to you, maybe there's some weird ones where it's impossible to put the numbers in, right? The fact that it was possible to do this, it's not obvious that's always going to be possible to label the arcs in this way with the numbers, all right? So the question is, given an at-most n-valued map, can we always assign the weights in this way? Again, this is like our main counterexample. This one, actually, you cannot assign the weights in this way. If you tried to, they would look something like this. Each arc has to have its own weight, and because of the circle thing, because this goes out here and comes back here, these would have to have the same weight. But you can see, if they were assigned in this way, then you have a problem with the additivity. Because, for instance, right at the top there, here, I have a C and a B meeting and coming out as a C. That means that C plus B has to equal C, but the weights are not allowed to be 0, and so this is not possible. So this right here cannot be realized as a weighted map, right? Let's think for a moment about what exactly does it take to be a weighted map. Like this one I showed you before, you can actually draw put weights on everything. I would say from kind of an intuitive level, what it means is there's some kind of like coherent way whereby I can say we must be able to decide which points are like single points versus double points versus triple points. Like, for instance, if you think of these as being like double points, it makes sense to split it apart into 2 single points, all right? And if I ask you, is it even possible to draw the weights there? Really, the question is like, is it actually possible to decide, like, this is a triple line, this is a double line, that's a single line. Those are both single lines, but this is a double line. This is a little complicated, but is it even possible to make a coherent decision in that way, all right? Is it possible to coherently decide which are single versus double, which are triple? And actually, if you think about it, this is exactly the same question that we had to deal with before about these symmetric product maps when I had, is it like 2 of this point and 1 of this point, or 1 of this point and 2 of this point? And is it even possible to do this in a consistent way? This is the vague idea, which hopefully will give you an idea that the continuity of the weights is actually equivalent to continuity as a symmetric product map. And so we were able to show that the class of symmetric product maps is actually the same as the class of weights. So if this business about symmetric product was too abstract for you, it's entirely equivalent to just being able to put those numbers on the graph. All right. This was kind of pleasing to me, I would say. Actually, in an earlier paper of Roberts, he already showed this. S is a subset of W. And so I saw that in the paper, and I was like, I got to call this guy. because I asked him, the first time I ever emailed him, I said, hey, I read this theorem you have. Did you ever try to prove the other way around? And he said, no, but together we showed that the other way around is also true. So these two sets are equal. I say together, meaning I asked him, hey, have you ever proved that? And like a couple weeks later, he wrote a proof and showed it to me. So this was our collaboration together. So anyway, everything that I've said so far all together is like this. I got about 5 more minutes. I think that's enough time to tell you about the last class, which is F. The F is the most technical of all of them, and I'm going to say the least about it, but it has some very weird examples. So the F, these are what we call the n-fold maps, and these are multi-valued functions that are defined in terms of n-fold covering spaces. This is a fairly standard topological thing that people talk about in algebraic topology. It's a concept where you can start with a topological space and you can create, say, something like a threefold cover, which means it's a copy of that space which has sort of 3 different copies of each point from the original space. So you can imagine something like, if you start with a circle, a threefold covering of a circle could be like a spiral sort of living upstairs above the circle, which has 3 layers. And those layers act like individual circles. Anyway, that's called a threefold covering space. The n-fold maps are defined in terms of n-fold covering spaces. The idea is you start with a space. If you want an n-valued map, it's the same as sort of copying the space n times and then choosing a single valued map. That's the idea. But anyway, once you understand what this means, it's, I say in quotes, easy to show this. Like, Dassyberg and I are very familiar with the classes F and S, and we more or less immediately realized that this must be true. The more difficult question is F equal to S or is F equal to the U? And I more or less, from day one, thought that F and S were equal. And I actually, when we started writing the paper, I wrote this in the paper as a theorem. And then in the proof, I wrote something like, Robert should fill this in later, or something like that. Like, I thought this was going to be more or less a routine to show that F and S were the same. I believe for a long while they were equal. It turns out they're not. So Dassyberg found a counterexample, and it's a weird counterexample. There is an example of a at most 2-valued map. This is from the 5-dimensional sphere to the 2-dimensional sphere. And this example, we can show that it is a legal map into the two-fold symmetric product, but it's not a 2-fold map in this covering space sense. Very strange, and this is an example I would have never come up with. Dassyberg is he knows much more about these high-dimensional spheres than I do, and I would have never come up with this example. And also, there is another example here from RP2, that's the real projected plane, to S2. We have an example which is a 2-fold map, but you cannot break it into a union of equicardinal. So that means this F really is sort of properly contained in between these other two classes of maps. All right, and this is really the full version of the theorem that you'll see in the paper. Some other things, we also give conditions on the domain. When you're talking about these functions from x to y, we give some conditions on x and y which will make it so that u and w are equal. That is to say, all of these, sometimes for certain types of spaces, they're actually all the same. They're not all the same for the circle. That's what all my counterexamples are. But for certain types of spaces, they are all the same. So, and we have some theorems to that end. And then we also talked about sort of a configuration space point of view. This is the configuration space of all at most n-valued maps into the circle, and we talked about the structure of that. But anyway, that's about all. Thank you for your attention. If you want to see the paper, you can check it out. Yeah, it's just called at most n-valued map. The end. Questions?
So do you have a theorem that says I lost you when you effed up, I lost you, that I can take care of.
When I effed up? Is that what you said? When I start talking about F. Yeah.
No, but anyhow, do you have a theorem that says a function is not divisible in pieces?
Mm-hmm.
If and only if, say, is, for example, from the circle, if it's only if it's made in a certain type, like in a certain way. I feel like I was thinking of your counterexample, And it seems to me that the function you cannot divide, there are really two functions, and then something that connect them in between, that it's not all over the domain. Every time you could do that, you can't divide it. Do you have a more general theorem that does that, or no?
No, we don't have theorems like that. But I think probably something like what you're saying is probably true. But yeah, you're talking about when you look at the graph, if you can view the graph as some arcs which have certain connectivity properties. Yeah, we didn't think at all in that way, but that's probably, yeah, there probably is some theorem like that. Yeah.
Thank you.
Thank you for your questions. Any others? No? All right. Well, thanks. That'll do it.